All right, so this chapter was about temperature um, and heat. Okay, you saw that uh, temperature was a measure of the average kinetic energy per particle. Temperature tells you how hot an object is, and what that measures is how much kinetic energy each particle has on the average. Notice every particle is not going at the same speed. Different particles have different energies, okay? But temperature measures what is the average kinetic energy. Okay? Now, here's an amazing thing. In solids, the atoms are at fixed locations, but they vibrate around their fixed location. And so the kinetic energy of those atoms is the same as the kinetic energy of the gas in this room because they're at the same temperature. Okay? And do you guys know how fast these gas molecules are moving? So in this room, they're moving at about half a kilometer a second. So each gas molecule in this room will go from here to Mainland High School in a second. That's how fast they're moving. Okay? All right, so temperature is a measure of the average kinetic energy per particle. We learned that. Okay? What I'm going to do is I'm going to quickly summarize what we did last week and then go over the new stuff. Okay? So two objects are in thermal contact when they can exchange heat energy. Okay? And like we said last time, you're in thermal contact with everything in this room. You can exchange heat via conduction, convection, and radiation. And we'll come to that. Okay. Some thermal contacts are stronger than others. Okay, so if you can exchange more heat, then the thermal contact is stronger. Okay. So for instance, this water bottle is in strong thermal contact with the table. It's in weak thermal contact with her. Because this bottle is exchanging electromagnetic radiation with each one of you. Okay. All right. Thermal equilibrium is when two objects are at the same temperature, there's no net exchange of heat. There's heat being exchanged, but there's no net exchange of heat. Yeah. Okay, so we learned this last time. This faucet and this table are at the same temperature. But this faucet feels colder. Why is that? Yep.
Because the metal of the faucet is a better conductor, so you lose that heat faster.
So what our friend is saying is, we're not a good thermometer. What we are better at sensing is the flow of heat. When I touch the faucet, I'm losing more heat faster, and that's what we are more sensitive to, even though these two are at the same temperature. Okay. When I touch this piece of wood, I'm not losing heat as fast, and so it doesn't feel as cold. You know? So that's what this slide tells you. Yeah. There are three commonly used temperature scales: Celsius, Fahrenheit, and Kelvin scale. We saw that the Fahrenheit scale was a finer scale, and so we use this to measure our body temperature and stuff like that. Okay. To make any temperature scale, what you need is two physical phenomena that happen at the same temperature. So for instance, ice melts at the same temperature no matter when. At one atmosphere pressure, you can melt ice in the middle of the night, during the day. 10 years from now, what you'll find is it melts at the same temperature, and you can call it whatever you want. Okay? So these guys call it 0 degrees Celsius. These guys call it 32 degrees Fahrenheit, and these guys call it 273 degrees Kelvin. The other phenomena we use is the boiling point of water. Okay. At 1 atmosphere, you boil water, you boil it today, tomorrow, in the middle of the night, it always boils at the same temperature, and you can call it, so these guys call that 100 degrees Celsius and so on. Okay? these two formula, this formula lets you convert from a Celsius temperature to a Fahrenheit temperature. So you can put, let's say 20 degrees Celsius, 20 divided by 5 would be 4. 9 times 4 is 36. 36 plus 2 is 68. 32, okay? So 20 degrees Celsius is 68 degree Fahrenheit, okay? So that's what this lets you do. And this lets you convert from Celsius to Kelvin scale. Okay, so temperature is a measure of the average kinetic energy per particle. Okay, so when you cool stuff down, what happens? The molecules slow down. And what is the best you can do? Stop them all. And that is the lowest temperature you could ever go. Okay, and that's absolute zero. Okay? So there's no lower temperature than that. And that's the absolute zero temperature. Okay. Here are some temperatures we measured. That's the interior of this, that's temperature. The interior of the sun, which is 15.6 million degree Kelvin. There's the temperature at the center of a hydrogen bomb explosion, 100 million degree Kelvin. And we talked about how do you measure the temperature of such an object. Remember, nobody puts a finger in the middle of an explosion. So how do you measure this temperature? What you do is you look at the radiation coming from the explosion. Okay. And we saw the black body curve, which is a very important curve. All right. So here's the hydrogen bomb exploding, and you're looking at radiation coming from the explosion. Okay, you're looking at this radiation, and here's what you do. Okay. So what this graph tells you is the intensity for versus wavelength. Wavelength tells you the color of light. Okay. The longer the wavelength, less energy the radiation has. Okay, and we'll learn about this. Okay, so at this wavelength you measure the intensity. At this wavelength you measure the intensity. At this wavelength you measure the intensity. And for every temperature, the curve is unique. Okay, so you change the temperature, the curve changes. Okay, so if you measure the intensity for 3 or 4 wavelengths, you know exactly what the temperature of the object is. Did you guys understand that? Okay. And we use this kind of stuff, those no-touch thermometers that people use. That's what that thermometer is doing. That's how it knows your body temperature. Okay. It's measuring the intensity for 2 or 3 different wavelengths. Okay. And then it sees which curve fits those intensities. Okay. So if you measure, so let me so you use that no-touch thermometer, and what the thermometer does is it measures the intensity for this wavelength, and for this wavelength, and then it fits a curve. And this corresponds to your body temperature. Okay? And that's how that temperature is measured.
So you're saying
The longer the wavelength, the less energy that radiation has. Okay. All right. So this is called the black body spectrum. Okay. So this is called the black body spectrum. All right. we saw that when you, so here's a model of a solid, okay, for a metal. In a solid, all the atoms are fixed, and the forces between the atoms are modeled by springs. Okay, these springs won't let this guy run away. And so when you heat a solid, all these guys vibrate with a larger amplitude, their energy increases. Okay? And like I said, temperature measures the average kinetic energy per particle. And also, when you heat, there's energy that goes into the spring which makes them expand, and the atoms go further apart. So a consequence of that is when you heat something, when you heat a metal, its length increases. Okay? And this table tells you how much the length increases. So a consequence of that is you have to account for that expansion, and so you leave gaps between spans on the bridge. Those are the expansion gaps that you see. Okay. So if you've ever walked across a bridge between spans, you can see that. So this is the gap is opened up in the winter, and look, the gap is closed in the summer. If that gap didn't exist, those spans would push against each other and the bridge would crumble. Okay? And that's what has happened here. You see on these train tracks, there's not enough gap between the rails, okay? And they pushed against each other and deformed, and this would lead to derailment. Okay? All right, when you heat this object again, this will vibrate with greater amplitude, it will expand, it'll have potential energy, kinetic energy, okay? And when you put this object in contact with the object of lower temperature, some of this energy flows into that object, and all that random kinetic energy and potential energy is heat. Okay. And heat flows to this guy till both the temperature of both the objects is the same. Okay. When the temperature of both the objects are the same, then the average kinetic energy and potential energy are the same, okay, per particle. So we saw all of that. So here's an important, this was sort of a long story we saw. When you heat an object, when you increase its temperature, for normal substances, when you increase its temperature, its volume increases, and density, which is mass divided by volume, decreases. Okay. So for almost all substances, when you increase temperature, volume increases and the density decreases. Now, water is a strange beast. For this temperature range, from 0 to 4 degrees Celsius, as you are increasing the temperature, look at the density, as you're increasing the temperature, instead of the density decreasing, it's increasing. It's a very small effect. It's 10 parts in 10,000. It's a very small effect. Okay? But this is what allows for lakes not to freeze during the winter. Okay? And you saw that. So lakes, only the top layer of lakes freeze, and this is important for life because then life can survive through the winter in the inside lakes. Okay, we saw that. And also an additional fact is when water freezes, ice is less dense than water, so that's an important fact as well. Okay, anybody remember what latent heat is? So we saw that last time. When you add heat to a substance, its temperature will increase. Yep. Now, is there any time when when you add heat to a substance and its temperature does not increase, its temperature does not, yeah.
Yeah, that's the latent heat when it's going through a phase change.
When a substance is going through a phase change, its temperature does not change. Okay? What do you mean by a phase change? When it's going from solid to liquid or liquid to gas phase, then its temperature is not changing. Okay? So when ice melts at 0 degrees Celsius, okay, you add heat to the ice, its temperature will not change till all of the ice melts. Okay? And you need to add, so this is called latent heat of fusion. For water, you need to add 80 calories of heat to melt 1 gram of ice. Okay? Similarly, if you have water at 100 degrees Celsius, if you're boiling water, let's say you put it on the stove, this is 100 degrees Celsius, this pan can still be on the stove and the temperature of water does not rise. Okay? What is happening to all of that heat? All of that heat is going into vaporizing the water. Okay? And to vaporize 1 gram of water, you need 540 calories of heat. Okay? So these are important numbers. This is an extremely important number to remember. Okay? So for instance, that's what we use. Evaporation of sweat is what you use mainly for cooling your body. Okay? Getting rid of excess heat from your body. So this is an extremely important number. All right. So that's latent heat. Latent heat is the heat added during phase change, and that heat does not change the temperature of the object. So here are the two numbers. For water, 80 calories of heat, you need 80 calories of heat to melt 1 gram of ice, and you need 540 calories of heat to vaporize 1 gram of water. And conversely, when water freezes, you have to remove 80 calories of heat, and when steam condenses, it gives up 540 calories of heat per gram of steam condensing. So that's why steam burns are extremely dangerous. Okay? They're depositing a lot of heat on you. Okay? All right, so here's latent heat of various materials. Okay, so that's what we did last time. And now we'll talk about new stuff. Okay? Okay, so first thing we'll talk about is evaporation. Okay. So let's say the temperature in this room is 20 degrees Celsius. Okay. I have a glass of water, and I'll set this glass of water on the desk here. It's 20 degrees Celsius. Will any water evaporate? Yes? Yeah, that's correct. Water will evaporate. Is there any circumstance when the water won't evaporate? So I'll put this, okay. So, look, okay, let's see why will it evaporate. This is important. Okay, so let's go back to our So you saw that you have a gas, and all these molecules are randomly moving, and they have kinetic energy based on the temperature. And you warm up the gas, you warm it up, and then the molecules move faster. So at any given temperature, there are gas molecules moving. Some are fast, some are slow. Okay? The temperature measures the average kinetic energy. Okay? So just like that, coming to this water, okay, all these water molecules are also moving. They have random speeds, and some of the fast ones will escape. Okay, and that's evaporation. Well, there's water molecules in the air as well, and some of those guys are hitting. Okay, and they're coming into the cup of water. Evaporation is when more are escaping than coming in. All right? All right, so if I set a glass in water in this room, there'll be water molecules evaporating and you're losing water. When will there be no evaporation? Yep.
The pressure's high enough?
When the humidity is 100%, then the number of water molecules escaping is equal to the number coming in. Okay? Remember, every time when 1 gram of water escapes, it takes away, evaporates, it takes away 540 calories of heat. Okay, so why do I mention this? Because that's your body's cooling mechanism. So if you're sweating, when do you get rid of heat? When the sweat evaporates. And now you just learned, when will your sweat not evaporate? When will your sweat not evaporate? When the humidity is 100%. Okay, so that's an extremely dangerous situation. Okay, and we'll see how you can solve that problem. Okay, so all right, so at any given temperature, water molecules are escaping and water molecules are coming in. If there's a net and more are escaping than coming in, then you have evaporation. Okay. Okay, so let's come to this. What I want to do is tell you about this fact. Okay, so water and other substances can evaporate at temperatures far below their boiling points. A glass of water will slowly evaporate away in few days. Okay. And if you want to make it evaporate faster, all you have to do is reduce the humidity in this room. Okay, the humidity in this room is about 40 to 50%. Yeah, that's a comfortable humidity. So ice sublimates directly to water vapor. So molecules from ice can go directly into water vapor. It can directly sublimate, and that's what happens. And so ice cube left in a freezer slowly disappear as water goes from its solid state directly to gaseous state. Okay, you guys have heard of self-defrosting freezers? You guys, so yes, no? Self-defrosting freezers. Okay, so okay, how do you defrost your freezer? You unplug it, bring out all the food and stuff like that, and your food might go bad. So there are such things as self-defrosting freezers. Okay, and what they'll do is, so the ice in the freezer will evaporate, and here's how it happens. Okay, and so, well, why is that a good thing? Because your food doesn't ruin. Okay? And all right, so here's what this graph says. So this is the phase diagram of water. Okay, what this tells you is this substance, H2O, in what phase can it be at these pressures and temperatures? Okay, so this is this diagram is a lot of information. It tells you, so for instance, at this pressure and this temperature, at this pressure and this temperature, and this point, that substance, water, can only be in the solid state. You can only have ice at that temperature and pressure. Okay, so let's say this is 1 atmosphere. At this temperature and pressure, you can have both water and ice. Okay, so that is 0 degrees Celsius and 1 atmosphere. So next time you see a glass of ice water, you know its temperature, exact temperature, it's 0 degrees Celsius. Okay, so at 1 atmosphere and 0 degrees Celsius, water can coexist in both solid and water phase, in liquid phase. Okay, so here's how the self-defrosting freezers work. Okay, in your freezer, the temperature is about minus 5 degrees Celsius, and so there's ice. Okay, and if you, okay, oh, well, so it's minus 5 degrees Celsius, and normally the pressure is higher. Okay, and what you do is, if you remove all the water vapor, this is the pressure of the water vapor in the freezer. If you decrease that pressure, and now it comes here to this point, it comes there, and now the ice can directly evaporate to vapor phase, and that's how you defrost it. Okay, so you remove the moisture. You remove the moisture from the freezer, and then the ice goes directly to the gas phase. Okay, so so that's how they defrost it. Okay, now here's another thing that this diagram shows you. All right, you guys know how skiing works? You guys, how many of you have skied? Okay.
I'm an active skier, so.
All right. So how does skiing work?
Well, I mean, depends on the friction, but
Yeah.
you basically have your skis that are on the snow, and they use a combination of friction and balance and whatnot to go on the snow. But sometimes the snow, it could be in different conditions. Sometimes it can be icy, so it's a little slippery. Sometimes it's fresh powder, so you get a bit more
Right.
traction and whatnot. So
All right. So here's how it works. So here's ice on the ground at that temperature. It's solid. Okay, and the friction is high. What you do is you get on your skis and you step on the ice. When you step on the ice, you have increased the pressure. So the pressure is increased. And what has happened to the ice now? So you got on the skis. So here's ice. You got on skis. You got on it, and you increase the pressure on this ice. The pressure increased, and the ice has become water. It's melted. Okay, so this ice melted, and now the friction is reduced. So that's melted water is like oil now, and now you can ski. Yep. So that's and so that is possible because this curve has a negative slope. Most substances have positive slope. Okay, and you couldn't ski in those conditions. So if you had alcoholized ice, for instance, you couldn't ski on that. Okay. So this negative slope was important. Anyway, all right. So let's get back to, okay. So what makes evaporation and sublimation possible at temperature below boiling point is random molecular motion. Okay. Those molecules with large enough kinetic energies overcome the attractive force of other molecules and escape as a gas. Okay. So evaporation happens when more molecules are escaping than coming in. Okay. Evaporation happens when the relative humidity is less than 100%. When humidity is 100%, number of molecules escaping is equal to the number of molecules coming in. Okay. So for instance, here's a closed container, and the water is boiling, and as many water molecules are going out as coming in. So there's no net evaporation. Okay. Okay, now we'll talk about relative humidity. which is when you say 50% humidity, what does that mean? When people say 60% humidity, what does that mean? Okay. So what this table tells you is at any given temperature, the atmosphere can hold a maximum number of maximum amount of water. So for instance, at 20 degrees Celsius, which is the temperature in this room, okay, at 20 degrees Celsius, the maximum water that the air can hold, that is 17.3 grams per meter cube. So a meter cube is this much air. This much is a meter cube. And 17 grams is roughly, well, a half an ounce. So roughly a mouthful of water. Okay, that's how much this much air can hold. That's the maximum. So now if there is half of that, if 17 grams, so if there is 8.65 grams of water per meter cube, then that would correspond to 50% humidity. Did you guys understand that? If it's holding half the maximum, then it's 50% humidity. If it's holding 25% the maximum, then it's 25% humidity. If it's holding 17.3 grams, that's 100% humidity. Okay? And that's important. Okay? All right, so a relative humidity of 100% means that the air is totally saturated and can hold no more water vapor. And why do we care about that? Well, if you sweat, your sweat is no longer going to evaporate. And yes, if your sweat is not evaporating, you're not getting rid of heat from your body. Okay? So no more evaporation can occur, and your sweat will not evaporate to cool you down. All right, so one example of low humidity is found in self-defrosting freezers. Okay? The problem is this can also dehydrate foods that are not properly sealed, and you get freezer burn. Okay. People find that they're most comfortable when air has a relative humidity of 40 to 50%. That's what we maintain in this room. Okay. Lower humidity dries out your skin and mucous membranes and cause sinus trouble and other respiratory problems. So that's why sometimes people have humidifiers in their rooms and stuff like that. Okay, if you suffer from if low humidity bothers you, higher humidity suppresses the net evaporation rate of perspiration, and may cause you to feel uncomfortably warm even in moderate temperatures. Okay, so if you're not your sweat is not evaporating, then you're feeling warm, and too low humidities will dry out your skin and mucous membranes. Okay? So you have to find, most people are comfortable with 40 to 50% humidity. Okay, we are warm-blooded animals, and we maintain a temperature of 37 degrees Celsius. Okay. If your body temperature becomes too high or too low, you can have irreversible damage can occur, and it can even be fatal. Okay, so you want to maintain a body temperature of 37 degrees Celsius. Okay. Look at this. If the body temperature rises above 42 degrees Celsius, okay, that's 5 degrees Celsius above that. So if your body temperature rises 15% above your normal temperature, okay, the body's cooling mechanism cannot keep up, and external intervention is needed. Okay. And so we'll see how to solve that problem. Okay. All right, cell metabolism increases with increasing temperature. So any reaction rate will increase with increasing temperature. Cell metabolism increases. Increased metabolism generates more than normal amounts of heat. So it's a vicious cycle. Yeah. If your body temperature is higher, you're producing more heat, and that's making the situation worse. Okay. So you're producing more heat, and a vicious cycle results. And above 42 degrees Celsius, the body's cooling mechanism fails, so 108 degree Fahrenheit. An external intervention such as alcohol rubs are necessary, and I'll show you a problem in that. An analogous problem exists when body temperatures become too low. Cell metabolism decreases, and insufficient body heat is produced to prevent body temperature from dropping further. Okay. So when the body temperature is lower, you're not producing enough heat, and your body temperature falls even further. Okay. So that's a vicious cycle as well. All right. So for a 130-pound person, the basal metabolic rate is about 80 watts. Okay. So when such a person runs, they would generate 1200 joules per second. That's 1200 watts. So the amount of heat production has increased by a factor of 15 times greater. Okay. So how do you remove the excess heat? What you do is you sweat, and every time 1 gram of sweat evaporates, it takes away 540 calories of heat. Okay? So that's your cooling mechanism. And that's a large amount of heat that's taken away. Okay? So it takes, okay. So when sweat evaporates, it removes heat from our bodies. Okay? So now you just learned, if you live in Florida and it's 100% humidity most of the time, you sweat and your sweat doesn't evaporate, what do you do? Okay? That's a problem. Okay. So so we'll see in a emergency situation what happens. So in addition to evaporation of perspiration from skin, there's a significant evaporation of water from the lungs. So every time, it doesn't matter where water evaporates from, 1 gram of water evaporating takes away 540 calories of heat, and that's a large amount of heat. Okay, so here's a situation. So 45 degrees ambient temperature. 45 degrees is 90. Well, this is quite warm, about 120 degree Fahrenheit. Okay, so on a very hot day, even if you're just sitting down, this is your basal metabolic rate. So you're just sitting, let's say outdoors, and it's very hot. You have to get rid of this heat. Okay, this is what your body is producing, because this is warmer than your temperature. Your heat is being conducted into your body. You're getting heat via radiation. So you're producing this much heat, you're getting in radiation. This is conduction, and this is hard to calculate, so you're getting convective heat as well. Okay. How do you maintain your body temperature? Okay. The only way to get rid of heat is by sweating, and for this sweat to evaporate. Okay, and that's what will take away your heat. Okay. Now, if you're at this temperature, if you're at a hotter temperature and if the humidity is 100%, it's goodbye. That would be very hard to survive. Okay, so when the outside temperature is higher than your body temperature, evaporation of sweat is the only mechanism of losing heat. Okay? So evaporation of sweat is the only method of cooling off that works when surrounding temperatures are warmer than body temperatures. Okay. So you saw that you sweat, and the sweat evaporates, your sweat evaporates, and every time 1 gram of sweat evaporates, 540 calories of heat are taken away. Okay, when will your sweat not evaporate? 100% humidity. And so if you have a situation when somebody is overheating and the humidity is very high and you want to cool them fast, what can you do? Alcohol rub. Okay, why do we do an alcohol rub? What's that? There's no alcohol in the atmosphere. Okay, you want something that will evaporate fast. Okay, and there's zero alcohol in the atmosphere. So you give them an alcohol rub, and the alcohol will evaporate. Oops. Okay. Are you in the? So when you give an alcohol rub, the only thing is when 1 gram of alcohol evaporates, it takes away only 240 calories of heat. Okay, so that's why we didn't evolve to sweat alcohol. Okay. When water evaporates, you take away more heat. Okay, so this problem shows. Okay, so it's 204 calories actually. So I was being generous there. So what this problem goes through is the following: 70 kg person. That's roughly my weight. 70 kg is my weight. Okay, if you want to reduce the temperature by 1.5 degrees Celsius. Okay, so let's say my body temperature goes to 42 degrees Celsius, and we need intervention. We need to reduce my body temperature fast, and what we're going to do is try and reduce it to 40.5 degrees Celsius. Okay. So one of the things to do is you can throw me in a pool and stuff like that, but if you don't have an ice bath, then you can go for an alcohol rub and stuff like that. Okay. So you want to reduce the temperature by that much. Here's the specific heat. Okay. So the amount of heat you want to remove, you just need to have a sense for this. So there is the mass, 70 kg. There is specific heat. Specific heat is that. Okay. So that's the mass converted to grams. There's the specific heat, calories per gram per degree Celsius. That's the specific heat of a body. And you want to reduce the temperature by 1.5 degrees Celsius. Okay. So the amount of, so this is the amount of heat you have to remove, which is that. And this is the heat of vaporization, or what I've been writing is latent heat of vaporization for alcohol. Okay. So the mass of our alcohol would be this divided by that divided by that. So there is that divided by, okay, this thing is missing this number. This problem is missing that number, 204 calories per gram. So that is needed. And so what you have to do is you have to apply 427 grams of alcohol. Okay, 427 grams of alcohol rub will reduce my body temperature by 1.5 degrees Celsius. Okay, and that'll happen fairly fast. And 427 grams is roughly, can you hold your coffee cup up? That much alcohol. Okay. Has anybody done this in the healthcare industry? Anybody aware of this?
Like one
Have you
time
seen?
we were hiking, used alcohol wipes to or something.
I'm sorry?
Well, like one time when me and my family were hiking, it was a little hot, so we had them on hand, alcohol wipes.
Oh, okay.
That was like once. That was only because we had a first aid kit, and we just kind of used it. We were just really not looking at any ice on us. I person to talk to. That was like once though.
Okay. That's interesting, but you were aware of this thing, this phenomenon.
Well, my dad was more aware
Okay.
than me. So,
All right. All right, so now we'll talk about heat transfer mechanisms. So here's a fire. If you hold a metal rod, you can feel the heat flow through this metal rod to you. That's heat transfer via conduction. Okay, so there are three mechanisms for heat transfer: conduction, convection, and radiation. Okay, so that's heat transfer via conduction. Okay, you hold your hand up there, you will feel the warmth. And how did you feel? How did heat get to you? I'm sorry? Okay, so this fire warmed the air around it, it expanded, and that warm air rises. Okay, so you got heat transfer via like that. So for that heat transfer, a fluid, which is air, actually moved. Okay? And you do this in your body as well. So when you want to get rid of heat, what happens? You make blood flow to your skin, you evaporate. Okay, so when fluid flows, that's convective heat transfer. Okay, now how did this warm air rise? Because warm air is less dense and it rose up, and that's how heat transfer happened. Okay, you can hold your hands on the side. Now warm air would rise up, so you're not getting convective heat, but you'll feel heat here, and that's because of electromagnetic radiation. Okay, so this diagram illustrates all three methods of heat transfer: conduction, convection, and radiative heat transfer. All right, so here is a solid. So if this end is hotter than this end, heat flows from the hotter end to the colder end. Okay. And how does heat flow? Okay, so hotter end means these molecules are vibrating with a larger amplitude. Colder means these guys are not vibrating with the larger they're vibrating with a smaller amplitude. These guys bump into the neighbors and transfer some of their heat. These guys bump into their neighbors, transfer some heat, and eventually heat gets there. Okay. And when does heat flow stop? When the temperature is uniform, when all the molecules have the same average kinetic energy. Okay. This tells you, again, you don't have to remember the formula, the rate of heat flow. How much heat is flowing per unit time, okay, per second. This is the thermal conductivity. A is the area of cross section. This is the temperature difference. Okay, higher the temperature difference, greater the heat flow, and D is the distance between the temperature difference. Okay, so if you want to decrease heat flow out, you increase the thickness of walls, for instance. Okay, and that's heat flow via conduction again. So again, you're just bumping into your neighbors and transferring energy to the neighbor. Okay, if you have more energy, you give up some, and so on. And then this guy gives some to his neighbors, and so on, until everybody has the same amount of energy. Okay, so this is socialism. Convective heat transfer. In convective heat transfer, substance actually moves to transport heat. Okay, so here's how you transfer heat here's how you warm up a room via a space heater. So when you turn on the heater, all the air around it warms up, it gets less dense, and it'll rise up. Okay. And so now you left a partial vacuum, and so cold air comes and replaces that. That gets warm, and so you set up this cycle. Okay. And eventually the entire room gets warm. Okay. So that's convective heat transfer. In a convective heat transfer, fluid actually flowed. Fluid actually was transported and transported heat. Okay. So an example of forced convection is blood circulation. This was natural convection. Okay, you warmed it up, it became less dense, and because of buoyancy, it moved. Okay, but in your body, your heart pumps blood. Okay, that's warm, and that is forced convection. Okay, so when you're using energy, when you're using doing work to make the fluid flow, that's forced convection. Okay. Is blood circulation, which can transfer heat from one part of the body to another. Okay. Blood flow can be increased or decreased to specific area depending on need. Okay. So when it's hot, what do? You increase blood flow to the skin. When it's cold, you decrease blood flow to the skin. Okay. When it's hot, you want to get rid of heat, so increase blood flow to the skin, you sweat more, and then the sweat evaporates. Okay. Okay. You've all heard of wind chill. So what this is showing you is, this is the air temperature this is the air temperature. Okay. So if the air temperature is minus 10 degrees Celsius or minus 10 degrees Celsius here, you feel minus 10 degrees Celsius. But now, if this wind were moving, if it were moving at 5 meters per second, that air would feel as if it's minus 21 degrees Celsius. If this wind were moving at 15 degrees Celsius, 15 meters per second, that temperature would feel minus 34 degrees Celsius. All right, why does it feel colder when the air is blowing? I'm sorry? Okay, so air is a very good insulator. Okay? Yeah.
Because there's more cold, I guess, material or air impacting you at once. Like, if you're just standing still, you're gonna just naturally heat up around you. But if it's moving, that heat gets lost, and there's just more stuff impacting you with the air, I guess, and it's just cooling you down faster because you have a lot more cold air hitting you, sucking out that heat from you faster than if it was just still and you were allowed to just heat up and there wasn't a constant circulation of hot heat and cold.
All right, so you're warm. Yeah. So let's say this is, hang on. So you're warm and this is cold air. So let's say this was at minus 10 degrees Celsius. Heat flows from your body, this warms up, okay? And air is a poor conductor, so heat would not flow as fast, okay? So this air warms up. Now, if there's a wind blowing, this air will move away. This air was warmer and it wouldn't conduct as much heat. You wouldn't lose as much heat. But if the wind was blowing, this air would move away. You replace it with cold air, and then you lose more heat, okay? And this wind blows away and you lose more heat, okay? So when it's windy, you're losing more heat, okay? And so it feels like at minus 10 degree air, blowing it, and if it's windy and it's 10 meters per second, 10 meters per second is 25 miles an hour. Okay, that's a fast wind. That'll feel like minus 29 degrees Celsius, okay? So minus 10 degree air blowing at 10 meters per second, you'll lose the same amount of heat as minus 29 degrees Celsius air that is still. Okay, so that's what wind chill means. Okay, so this temperature air moving at that speed feels you would lose the same amount of heat as minus 29 degrees air that is still. Okay, so that's what wind chill means. Did you guys understand that? All right. You can lose heat via electromagnetic radiation. Okay. So we all emit electromagnetic radiation, okay, and this is true for babies, and they can lose a lot of heat via electromagnetic radiation because when you're small, your surface area to volume ratio is high, okay, and so you got to be careful. All right, this is your body temperature. The amount of heat lost is your body temperature to the power 4. Okay, this is called the emissivity. That's a constant called the Stefan-Boltzmann's constant, and this is your surface area. Okay. Now so in this room, of course, you're losing heat via electromagnetic radiation, and the walls are emitting electromagnetic radiation, and you're getting from that. So the net loss is if the temperature of the wall is less than your body temperature, then you're losing. There's a net amount of loss. If the surrounding temperature is higher, then there's a net gain of heat. Okay? So you saw that in this example. When the surrounding temperature was high, radiation, you were net gaining energy via radiation. See, this is a significant amount. With the surrounding temperature of 120 degrees Fahrenheit, this is higher than your basal metabolic rate. You see that? You're gaining more energy via electromagnetic radiation than you're producing in your body. Okay? So that can be significant amount of heat. All right, so this tells you, so this is your temperature, this is the surrounding temperature. And if the surrounding temperature is higher, you're gaining, so this would be negative, and the loss is negative, so meaning you're gaining heat. Okay. And okay, so this ideal absorbers and reflectors. Ideal absorbers are if you absorb all the radiation that's falling on you, you're an ideal absorber, and that emissivity, this guy is 1. When you absorb everything, emissivity is 1. And if you reflect everything that's falling on you, then emissivity is 0. Dark fabrics are good absorbers. Okay, so that's why in the winter you want to wear dark fabric. And in the summer, you want to wear white fabric because white fabric are good reflectors. Okay? So while light-colored fabric are better reflectors. All right, so okay. Now, handling cold temperatures. When the surrounding temperatures are low, it's necessary to limit rate of heat loss of the body. You don't sweat as much. So you don't lose heat, and then thick layer of clothing is necessary. Okay. You reduce heat transfer by conduction, convection, and radiation. Okay. So now you guys intuitively know this. Okay. Okay. So let's say it's cold, and what would you rather do? I'm just making up stuff. Would you rather wear a 1-inch thick blanket or 2 half-inch thick blankets, sweaters? So, would you rather wear a 1-inch thick sweater or 2 half-inch thick sweaters? Why? I'm sorry?
Layers, insulation.
Okay, why?
Because it's air trapping the heat.
There you go. So air is a very poor conductor. Okay. So what you want to do is you want to trap air between. That's why we wear layers. Okay. And what you want is you want to minimize heat loss via convection. You want to trap air, and you don't want the air to move. That's why you have these multi-layered windows, and that's what that is about. Okay. So that's why we wear layers. Okay. So you want to minimize when the temperatures are cold. You want to do everything to minimize heat loss via conduction, convection, and radiation. You don't want to sweat. You want to minimize conductive heat loss. Okay, and with insufficient clothing, the body loses much more heat than it produces. Its temperature drops, and uncontrollable shivering sets in. Here's an amazing number about shivering. Okay. Shivering is a clever use of opposing muscles to do work against one another. So you're not doing any mechanical work, but you're producing heat. Okay. Energy consumption during shivering is about 425 watts, the same as cycling. Okay, so you can shiver hard enough where you're using this, producing the same amount of energy as cycling. Okay. And you can rub your hands together to produce heat. Okay. All right, what is frostbite? So when water freezes, okay, when it goes to ice, it expands and its volume increases by 10%. Okay, so when water freezes, its volume increases by 10%. So for instance, in your cell, if you freeze the water inside a cell, its volume would increase and that would kill the cell. It would burst the cell open. Okay. So damage done to foods when frozen is due to primarily due to cells bursting by the expansion of water turned to ice. Okay. So that's why frostbite is dangerous. Some foods tolerate being frozen better than others, but none tolerate repeated freezing until thawing. Okay, so this is normal skin, early stages of that's a frost nip, and this is deep frostbite. A lot of cells have died. Okay. We use heat for therapies. We use heat as a therapeutic device. Okay, so the mechanism of relief by elevated temperature seems to be twofold. When you apply heat, your muscles relax, and increased blood flow is therapeutic. Okay, so that's why you apply heat, relaxation of muscle and increased blood flow, and so that's that's therapy for sore muscles. Okay, sometimes we also do removal of heat can also be therapeutic value. Okay, lower temperature acts as a local anesthesia, so it numbs nerves. Yes, so that's why you apply cold packs. Swelling can sometimes be reduced by application of ice packs. Okay, now here's an important fact for newborns. Heat transfer by radiation is also feasible. Heat lamps emit most of their energy in the form of infrared radiation, which penetrates your body. Okay. Newborn infants are sometimes placed under IR infrared heaters to replace the heat they would have received from their mothers. Okay. Within a few hours of birth, an infant's temperature control mechanism works well enough that the heater is no longer needed. So for some infants, their temperature control mechanism is not working properly, and so you place them under infrared lamps. Okay. All right, so that finishes